All right, let's get right into it. Today, we're looking at some absolutely fascinating research out of MIT that totally changes the game on how we think about our biggest, most powerful AIs. It turns out there's a massive, hidden flaw that nobody's really talking about, and it's a big deal.
So here's the big question, right? We keep hearing about these AI models with these gigantic context windows. We're talking millions of tokens, basically the equivalent of entire libraries. They're supposed to have these perfect photographic memories. But then you give them a genuinely complex reasoning task. Something like reading a 1,000-page financial report and identifying every instance of risk. And they just fall apart. So what gives? Well, the MIT researchers gave this problem a name, and it's perfect. Context rot. I love that term. And here's what it means. As you stuff more and more information into an LLM's prompt, its ability to actually think about that information doesn't just get a little bit worse. It hits a brick wall and just collapses. More data is actually making it dumber, not smarter. And this is where you can kind of see let's call it the marketing trick. Companies love to show off what's called the needle in a haystack test. Can the AI find one specific sentence hidden inside the entire works of Shakespeare? And yeah, they're amazing at that, near 100% success. But that's just a search function. The real test, the one that matters for actual reasoning, is something like the Ohlong-Paris test. This requires the model to compare every piece of information to every other piece of information. And on this kind of task, the models just, they tank hard. And wow, this chart just lays it all bare. Look at this. For a top-tier model like GPT-5, even on a pretty simple reasoning task, performance is already struggling at just 16,000 tokens. But for that really hard, complex reasoning, by the time you hit 33,000 tokens, which is way, way less than its advertised maximum, its success rate plummets to basically zero. It becomes useless long before it's even supposed to break a sweat. Insane. Okay, so we've got a huge problem, but the great thing is MIT didn't just point out the flaw. They came up with an unbelievably clever and elegant solution. And get this, it's not some brand new futuristic AI that'll be ready in 10 years. It's a totally new way to use the AIs we have right now. And this right here, this quote is the whole idea in a nutshell. It's brilliant. Instead of trying to cram a massive book's worth of information into the AI's short-term thought process all at once, what if you just treat that massive document like a file on a hard drive, something external that the AI can work with? Let me break it down using a computer analogy, because it makes perfect sense. Think of your huge document, your prompt, as a giant file on your computer's hard drive. This new method, which they call a Recursive Language Model, or RLM, acts like the computer's operating system. It just pulls in one little page of that file into its short-term memory, or RAM. Then the LLM, acting like the CPU, only has to process that one tiny, manageable chunk. It does its thing, saves the result, wipes its memory clean, and then loads up the next page. It's just so simple. It's genius. Okay, that's the big idea. But how does it actually work? Like, what's happening under the hood? Well, the secret sauce is this really cool idea called a neuro-symbolic system. And it's all about letting the AI, delegate the hard stuff to simple, reliable code. The big idea is just so simple. You let the large language model do what it's amazing at, understanding human language, spotting patterns, being creative. And then you let good old-fashioned code do what it's amazing at. The boring, repetitive, but super precise stuff, like looping through data and making sure you don't miss anything. You're just playing to each of their strengths. So check this out. It happens in 4 stages. First, the main LLM acts like a project manager. It actually writes a little piece of Python code to poke at the data and figure out how it's structured. Then, second, it writes another piece of code, a simple loop, to break the big problem down into small, bite-sized chunks. But step 3, this is where the magic really happens. Recursion. Inside that loop, it literally spins up a fresh, clean copy of itself to look at just one tiny piece of the puzzle. Then finally, the main LLM gathers up all the little answers from its clones and puts them all together into one final smart response.
All right, so the theory sounds amazing, right? But, does it actually work in the real world? Well, the results, they're not just good. They are absolutely jaw-dropping.
So remember that brutal Ohlong-Paris test we talked about? The one where a standard GPT-5 basically failed completely? Its success rate was 0.04%. I mean, that's essentially zero. But you take that exact same model and just wrap it in this new RLM strategy, and the success rate skyrockets to 58%. That's a performance gain of, get this, a 145,000%. I had to read that twice. It's just mind-blowing. Okay, I know exactly what you're thinking right now. This has got to cost a fortune, right? Well, this is the best part. For this specific test, the cost only doubled. It went from 16 cents to 33 cents. So for a 2 times increase in cost, you get a 1,450 times improvement in whether it actually works or not. I mean, who wouldn't take that deal? It's a total no-brainer.
So what does this actually mean in the real world? It means that using this strategy, we can now do real, complex reasoning on over 1 million tokens of information. And not in some future model, but right now, with the tools we already have. The whole context window barrier has basically just been smashed for this entire class of problems.
So look, this is way more than just a cool trick. What this MIT research is showing us is a massive shift in how we should be thinking about AI. It's a new blueprint for building smarter, more reliable systems, and it's all pointing in one direction, what the experts are calling a neurosymbolic future. For years, the entire field of modern AI has been dominated by this one idea from a famous paper titled "Attention is All You Need." It's been the guiding principle. And this MIT research basically comes along and says, well, actually, for the really hard stuff, attention is not all you need. And that brings us to this key idea, a neurosymbolic system. Think of it as the best of both worlds. You're combining the incredible fuzzy intuition of a neural network, its ability to understand language and context, with the rigid, logical, and 100% reliable power of traditional code. So this really flips the roles on their head. The LLM isn't the one doing all the grunt work anymore. It's the architect, the planner. It designs the strategy. And code, like Python, becomes the workhorse, the engine that executes that plan perfectly. And this is huge. Unlike other popular methods like RAG that kind of guess and hope they find the right info, this is deterministic. That code guarantees it will check every single piece of data every time. So if you're building with AI, the takeaway is stop trying to make your prompt bigger and start thinking like a system architect. And I gotta say, I love the way the MIT paper sums it all up. They conclude that for these huge, complex reasoning tasks that we need for science and law and medicine, neural nets just can't do it alone. They need a symbolic exoskeleton. What a great image, right? A rigid, logical structure of code that wraps around them and helps them do the heavy lifting. Which brings us to a really mind-bending final question. For years, the big race in AI has been all about who can build the biggest context window. But if this method basically makes the context window infinite, if it's no longer the problem, what's the new bottleneck? What's the next big problem to solve? It totally reframes the race for what's next in AI. Thanks for digging into this with me.